Welcome to This Explainer. Today, we're diving into a detailed, beginner-friendly university lecture on Chapter 7 from Cornell and Morris. We are focusing on the absolute foundation of any database system, structured query language, or as it's universally known, SQL. Honestly, whether you're aiming for a career as a database professional or a software engineer, really understanding SQL is just non-negotiable. It's literally the lifeblood of data retrieval and manipulation. So grab your notes, get comfortable, and let's master these essential concepts together.
Right, let's take a quick look at our course syllabus for the day. We'll be stepping sequentially through an introduction to SQL, the anatomy of a select query, filtering data, joining tables, aggregates and grouping, and finally, subqueries and a lesson summary. We're going to build your knowledge layer by layer.
Okay, Section 1, Introduction to SQL. Let's begin by setting the foundation of what SQL actually is and why it's the most critical tool for managing your database system's behavior.
So the crucial concept to grasp right off the bat is that SQL is a non-procedural language. Now, if you've ever written code in, say, Java or Python, you're used to procedural languages. In those, you have to spell out every single step the computer must take to achieve a result. Well, SQL is entirely different. Think of it like being a customer in a restaurant. You simply look at the menu and tell the waiter exactly what you want. You don't go into the kitchen and tell the chef how to cook it, right? In SQL, you just tell the database what data you need, and you let the system's internal optimizer figure out exactly how to navigate the complex data structures to cook it up and serve it to you.
Now, SQL isn't just one narrow thing. It's a vast language divided into a few key command categories. First up, we have data manipulation language, or DML. This is what we use to insert, update, delete, and most importantly, retrieve the data itself. Then there's data definition language, or DDL, which allows us to actually build the structural blueprints of the database, like creating tables and indexes. We also have transaction control language, TCL, which lets us permanently save or roll back changes. And finally, data control language, DCL, used to manage user access and system security. For today's lecture, our main focus is going to be firmly on the most common DML task, data retrieval.
Moving right along to Section 2, the anatomy of a select query. Let's look at the primary tool you'll use for that data retrieval.
To construct a proper, working request for data, you must strictly memorize this unshakable grammatical order of operations. Getting this right is absolutely crucial to retrieving information without throwing syntax errors. You always start with select, which tells the system exactly what columns you want to see. Next is from, to specify which table the data lives in. Then comes where, which filters the individual rows based on a specific condition. After that, we have group by, which gathers those filtered rows into specific buckets or categories. Having then acts as a filter for those grouped buckets. And finally, order by sorts your final output before it's displayed on the screen. Building your query step by step in this exact sequence is the secret to clean, functioning SQL.
All right, Section 3, Filtering Data. Now that we know the overall structure, let's look at how to selectively pull exactly the data we need using that where clause.
Beyond your basic equals, less than, or greater than signs, SQL provides some incredibly powerful special operators to filter your data dynamically. For instance, you can use between to find numbers or dates that fall within a specific range. You can use in to check if a value matches a provided list of specific options. You can even use wildcards with the like operator. For example, using a % sign to find a substring, like searching for any customer whose last name starts with Smith, regardless of how it ends. And critically, you can use is null to check for the total absence of data in a field.
Speaking of null, we really need to minimize a very common beginner trap right here. In database logic, null is not a zero, and it is definitely not a blank space. It represents the absolute absence of a value. It means that data is entirely unknown. Now, because it is unknown, you can never mathematically say it is equal to anything. If you make the mistake of typing where column equals null, the database evaluates that as unknown, and since it isn't explicitly true, it will just return 0 rows. You must absolutely prioritize using the is null operator instead, which correctly evaluates whether a field is empty, giving you a proper true or false result.
To put that into perspective, imagine looking at a table where the vendor code is simply missing for certain tool products. Using the is null operator is literally the only mathematically logical way to ask the database to return those specific empty rows.
Typing v_code is null will instantly isolate those products that haven't been assigned a vendor yet, whereas v_code equals null would fail completely.
Let's transition to Section 4, Joining Tables. This is a big one, because proper database normalization broke our data apart into many separate, efficient tables. We must use joins to put it all back together for our end users.
So, the absolutely crucial point here is that you must always use the modern join-on syntax. In the old days, programmers used what we call old-style joins, where they listed all the tables separated by commas in the from clause and then just dumped all the join conditions down into the where clause. Let me tell you, this is dangerous. It mixes the structural linking of your tables directly with your business filtering rules. It makes the code incredibly hard to maintain and can lead to massive data errors if a single condition is accidentally deleted. The modern join-on syntax forces you to declare exactly how two tables relate right up there in the from clause, keeping your code clean, safe, and highly logical.
When executed properly, this modern join-on syntax seamlessly merges columns from completely separate tables, like pulling together an invoice table, a line item table, and a product table into a single, highly readable report. By linking primary keys to foreign keys, the database management system seamlessly stitches the data back together. And remember, standard inner joins only keep rows that have a direct match in both tables. But we also have outer joins, like the left join and right join, which purposely keep the unmatched rows from one side of the relationship. That's perfect for when you want, say, a list of all your customers, including the ones who haven't actually made a purchase yet.
Okay, moving to Section 5, Aggregates and Grouping. Let's see how this builds into generating summaries using mathematical functions and buckets, shifting our focus from individual rows to high-level reporting.
These core aggregate functions are incredibly powerful because their specific behavior reduces an entire collection of rows down to just one single, neat summary row. Instead of looking at 1,000 individual product prices, you can use sum to see the total overall inventory value. You can use average to find the arithmetic mean price. You can use min or max to find the absolute cheapest or most expensive items in your catalog. And you use count to simply tally up exactly how many products you actually have.
But you might be wondering, what if you don't want just one massive overall average? What if you want the average price per vendor? Well, when you combine these aggregates with a group by clause, you can bucket your data. By stating group by vendor code, the database gathers all the products supplied by a specific vendor into a temporary bucket. And then it calculates the average product price uniquely for each of those buckets. The output, a beautifully organized list of unique vendors and their respective average prices.
Now pay close attention, because this brings us to a classic exam question, and a concept students mix up all the time. You must recognize the exact difference between the where clause and the having clause. Remember that the where clause filters individual raw rows before any grouping even takes place. Therefore, a where clause can literally never contain an aggregate function. The having clause, on the other hand, is explicitly required to filter the aggregated buckets after they are grouped. So if you only want to see vendors whose average grouped price is greater than $10, that condition must, without a doubt, go in the having clause.
Finally, Section 6, Subqueries and Lesson Summary. Let's take everything we've learned so far and see how we can start nesting queries inside of each other to solve really complex, multi-step problems.
A subquery is quite simply a select statement embedded directly inside another select statement. It allows you to process data based on values you don't even know yet. For example, what if you want to find all products priced above the overall company average? Well, you don't know what that average is yet, right? So you write an inner query to calculate it. That inner query does the heavy lifting first, finishes its job, and passes its single result outward to the main query, which then uses it to filter the final list. It's like a query within a query. You absolutely must recognize the difference between the two main types of subqueries. The one I just described is an uncorrelated subquery. It executes just once, totally independently, and hands its final answer to the outer query. But a correlated subquery is different. It relates directly to a column in the outer query. Because of this dependency, it acts just like a program loop. It doesn't just run once. It literally executes repeatedly, over and over, for every single row that the outer query is looking at.
To make that concrete, let's imagine a correlated subquery in action. Suppose you want to find sales where the units sold were greater than the average for that specific product, not the average of all products combined. The outer query looks at a row for a hammer. The inner query then dynamically calculates the average sales specifically for hammers and compares it. Then the outer query moves to a row for a saw, and the inner query recalculates the average specifically for saws.
It computes this dynamically on the fly to filter our results line by line.
Okay, to briefly recap before we finish, these are the absolute most important definitions, concepts, and key facts from Chapter 7 that you are guaranteed to see in your university exams. Remember SQL's non-procedural nature. Tell it what, not how. Burn that 6-step query order into your memory. Never try to say something equals null. Use is null. Always prioritize the modern join on syntax for safety. Understand the strict timeline difference between where and having. And grasp how a correlated subquery acts as a program loop, row by row.
We have established a really solid foundation in data retrieval using DML today. You now have the fundamental tools to ask the database almost any question you can think of. But I want to leave you with this final provocative thought. How do we actually create the tables we've been querying all day? How do we assign specific data types, build strict constraints, and securely lock down our system? Keep that question in mind because it perfectly prepares you for our next software engineering topic, Advanced SQL and Database Design. Thank you so much for joining this explainer, and happy studying!